Welcome once again to our discussion on panel data model, right? In our last class, we were discussing about first differencing to remove that unobserved individual specific time constant effect from our model, right? So, we were basically discussing about panel data, and that too we are discussing fixed effect model. That means our model was YIT equals to beta 1, let us say beta 0 plus beta 1 xit. Let us say that we have only one explanatory variable, and then we have ai plus uit. Okay, all right. And additionally, we had d t, that is one dummy variable, plus uit. And then we said that to remove this ai, what we did actually, we took the first difference of this model, and then ultimately our model become delta yi equals to some constant beta 0. This is, let us say, constant plus beta 1 delta xi plus delta ui. Okay, all right, where delta yi means basically yit minus 1, delta xi means xit minus 1, and delta ui means uit minus 1, right? Now, this is called first difference. First difference model, and though we can apply OLS here, there are certain limitations in this first difference model. What are those that we have to keep in mind? Limitations of the first difference panel data model. Firstly, there should be enough variation in delta xi across several individuals, several cross sections. Okay, this is the primary requirement. Whenever we include a variable as an explanatory variable in the model, the prerequisite is that there should be enough variation in that explanatory variable. Since here delta xi is the explanatory variable, what do you want? There should be enough variation in delta xi. So, that means to have enough variation in delta xi, we cannot include any time constant explanatory variable in our model. Okay, because if there is any time constant variable, that will get eliminated along with this ai while taking the first difference. Then secondly, we also mentioned that there should not be any lag dependent variable in our model. Okay, because if there is lag dependent variable, then let us say we have yit minus 1, then again we will get the endogeneity problem, because our error term has now become delta ui, which is uit minus 1. So, this uit minus 1 will obviously will get correlated with yt minus 1. Okay. So, that is why there should not be any lag dependent variable as explanatory in the set of explanatory variable in our model. Then the third limitation that we have not discussed is that in presence of measurement error, first difference produces significant bias in the estimates. So, these are the three major limitations in the first difference panel data model, because of which what we do, econometrician they suggest another type of transformation of this model, right. Let us see what is that transformed model. So, let us say that this is yit equals to, let us say, beta 0 plus beta 1 xit plus ai plus uit. This is the model. Okay, this is the model. And then what we do, we take time domain variable for time domain transformation for both yit and xit. What does it mean? Let us say that yi bar is defined as 1 by t summation yit, where t running from 1 to t. Okay. So, that means we are taking average of yit over time. So, that is why sum of yit divided by t is defined as yi bar. Similarly, xi bar equals to 1 by t sum of xit, t running from 1 to t. Then instead of taking first difference, what we do? We do this transformation yit minus yi bar equals to beta 1 xit minus xi bar plus uit minus ui bar. So, in this process, when we are transforming this variable in this way, then what is happening? This constant term and this ai, they get eliminated. Okay. And then what we get? We get this model. Let us write this is yit this equals to beta 1 xit plus uit, where this is defined as yit minus yi bar, this is defined as xit minus xi bar, and this is defined as UIT minus UI bar. Okay. So, this model is also known as fixed effect transformation, or within effect model. Within effect model. Now, why this within effect? We need to understand. So, here in this model, what we are trying to explain? We are trying to explain the variation in Y, which is time domain. Okay? So, that means we are trying to explain the time domain variation in Y with the help of time domain Xi. Okay? So, YIT minus YI bar is actually time domain variation in YIT. Okay, time domain variation in YIT. Hello. You come now. Yeah, you come. Okay, directly come. Yeah, IIT campus. Yeah. Okay. So, this is called time domain variation in YIT, and then XIT minus XI bar is time domain variation in XIT. Okay. Sorry, this is not actually YIT, this is YI, because we are already taking the time domain variation. So, YI and XI. So, for each and every cross section, we are trying to understand how in a particular year's YIT value is deviating from its mean in simple terms. For example, if I have income and consumption data, what is my transform variable now? How each and every year we have a value for YIT, how that value is differing from the mean. Okay. So, YI bar is the mean of YIT. So, that means in a particular year, let us say my consumption is 750 and my average consumption is, let us say, 500. So, 750 minus 500, that is basically YIT minus YI bar. So, this I am calculating for each year and then for each individual. So, for each individual I am trying to explain why there is some kind of variation in that YIT minus YI bar. So, instead of explaining YIT, we have to keep in mind now our dependent variable has become YIT minus YI bar. Similarly, what I am trying to, what is my explanatory variable? Instead of XIT, this is now XIT minus XI bar. Okay, XIT minus XI bar. That is my new explanatory variable. So, that is why I say that with the help of time domain X, I am going to explain time domain Y. Variation in time domain Y is explained by variation in time domain X. Okay, not like our standard econometric model where we try to explain variation in Y itself with the help of variation in X. So, that is the major difference we have to keep in mind. Okay, all right. So, from the structure of this model, once again it is very clear that in this model also, in this fixed effect transformation, what we did, again we cannot include any variable which is not changing over a period of time, because if the variable is time constant, then that variable will get eliminated along with the AI. And why this is called within effect model? Because this transformation yit minus yi bar, this I am calculating for each and every individual. So that means within the same individual itself, I am calculating the time domain variation. If I take ith individual, then I have ith individual's mean income or mean consumption, I have ith individual's over a period of consumption, and then I will just take the deviation of that each and every period's consumption from the mean. Hello? Okay. Now, we may think of that this fixed effect model has a limitation that we cannot include. What is the limitation then? We cannot include time constant explanatory variable. Okay, this is the limitation. But you may think of that what is the objective of the fixed effect model? My objective of this fixed effect model is to explain time variation in y with the help of time variation in x. If that is the objective, is it really a limitation of this fixed effect model? I am trying to explain the time variation in y with the help of time variation in x. If that is the case, then some variable which is not, for which there is no time variation, if over a period there is no change, why should I include that? Okay. So, even though this is the limitation of this model, we have to think that what is the objective of this fixed effect model. It is to explain the time variation in y, which is defined as yit minus yi bar with the help of xit minus xi bar. Okay. That is why we can't include time constant explanatory variable in this model. Okay. So, if any variable, let us say gender or any variable which is dummy, qualitative dummy, which are not changing over a period of time, those variables we cannot include in fixed effect model, right. Now, what we will do, we will take a simple data set and then I will take you through this fixed effect model, particularly how to basically estimate a fixed effect model. Let us say we have one data set, this is the data set. This is the data set, I will show you the data. This is the data. So, we have data for period 1997 to 1997, 1998, 1999. So, we have 3 periods data 87, 88, 89, 87, 88, 89. And what is this data about? This data is about how an employee's performance. These employees are working in, let us say, in a manufacturing firm, and in the process of manufacturing a product, the employees, they will produce some amount of scrap items, defective items, because of their lower amount of knowledge in the production process. They are inefficient. So, their inefficiency leads to defective production of items. And every year this company, they send some of their employees for some job training. And what is the objective? When you have that job training, then with the help of this job training, the efficiency of the employees improve, and number of defective item production also goes down. That is the hypothesis. And how many employees will be sent for this type of training program? That actually depends on what is the amount of grant that the company, what is the amount of grant that the firm is receiving. That is the major determinants. So, here we will try to understand the impact of that training actually on employees' performance. Impact of training on employees' performance. We have several variables, but we are not going to include each and every variable. Rather, we will take only number of scrap item, how that is related to training actually, which is again determined by the grant. All right. So, here what we do, our model is then YIT. So, YIT here is basically is, let us say, L of scrap item, SC scrap. L means this is logarithmic form I have taken, plus beta 1 grant IT plus beta 2 grant IT minus 1 plus UIT. This is our model. Grant, and we have included lagged variable also, because we believe that this year grant is related to some way or the other how the previous year's grant. So, that means this year's this production, this year's employees performance, that depends on last year's training program as well. Okay, last year's training program. That is why we have taken the lagged independent variable also, because if at all we believe that your training will give you some impact only after some time lag. So, if I receive the training this year, probably I will show the improvement in my performance in terms of manufacturing in next year, okay, in next year, right. So, that is why grant IT, this year's training is there and previous year's training is also there as independent explanatory variable. So, what we will do, we will try to explain this model using a fixed effect transformation. So, this is the data, and how will you estimate the model? Now, in Stata, when we estimate a panel data model, first of all we need to explain Stata that actually we are estimating a panel data model. And how will you estimate? You have to explain the nature of the data set to Stata. How will you explain the nature? The idea is TS set, sorry, XT set, this is the first command. X is for cross section, T is for time series. So, that means you have to specify what is your X variable, what is your time variable, what is your cross sectional variable, what is your time series variable. That command is given by XT set. Now, if you look at the data once again, see here your time variable is given by ER and your cross sectional variable is given by F code. Okay. So, here X is F code and T is ER. So, when I am saying XT set, you have to say F code and ER. X is for F code and T is ER is for T. So, that is why XT set F code ER if I put, then Stata will understand that. See what the Stata understand, it is a panel variable is F code panel variable, that means the individual specific entity wise variable is F code, that is the farm code. F code means farm code, right? I have several farms and you have to code 1, 2, 3, 4. So, if you go to the data again, see how the data is coding is. See, this is a specific code. This is a specific code they have given 41000032. That is some farm code 41000032, 41000032. So, that means in all the year the same farm. Then again 1987 41000040, 88 410440, 89 410440. Then again 87 another farm 410495, 88 410495, 89 410495, right. So, this is how you have to actually create a panel in Excel before you actually estimate the data. Okay. So, now I have explained, I have classified my data as a panel, and then what we have to do, we have to specify the regression as XT-reg. Instead of reg, now you have to put XT-reg. Why XT-reg? Because this is now a panel regression, not the ordinary least square estimation what we learned earlier. XT-reg, then you have what is your dependent variable, that is L scrap, right, L scrap, and then you have to put grant where is the grant? Grant is here, and then grant, this is this, and then you have to specify that this is a fixed effect model. How will you specify? You have to put one comma and then FE. FE is for fixed effect. Okay, this is how we need to explain. Now, this is the data. This is the estimate what we got. All right. Now, first of all, if you look at the grant as well as previous year's grant, they are significant. Okay. The first grant is significant, both are significant at 1% level. So, we can say that job training has some impact on the laborer's performance. Is that fine? Now, in this model, one thing is surprising. See, if you look at the theoretical model here, this is the model YIT minus YI bar equals to beta 1 XIT minus XI bar plus UIT minus UI bar. So, in this equation, there is no constant term. There is no constant term here. Now, if the constant term is not here, Stata, how come Stata is reporting a constant here? Look at here, there is a constant. So, that means the Stata's output is not going in accordance with the theoretical model what we set up for the fixed effect transformation. In the fixed effect transformation, there is no constant, but here we see that in Stata there is a presence of a constant term. What does it mean? It means either Stata is committing some mistake or we are doing some mistake in our theoretical structure. But our theoretical structure is very clear, there is no scope for any mistake there. So, what we can do actually, is basically we can understand the presence of constant term by another interpretation of the fixed effect model. The fixed effect transformation, what we do, this is the modern version of the fixed effect transformation. but there is some old version of fixed effect model also. Old version of FE. What is that? If we look at YIT equals to beta 0 plus beta 1 XIT plus AI plus UIT. Now, instead of removing this AI from the model, there is another way to estimate this model. Assume AI is a parameter to be estimated. Why AI is a parameter? Because AI basically indicates unobserved individual specific time constant effect. So, some way or the other, we are trying to accommodate the fact that individuals are different in terms of their some kind of unobserved effect. When we are estimating this type of job this type of labor performance, apart from your training, so on and so forth, whatever is there, every individual, every employee, he or she might be having some amount of individual specific, very individual specific intrinsic skill which is difficult to observe. And that skill, that innate skill generally does not change over time. At least over a period of 5 or 10 years, that would be constant. After that, it might get changed. As you grow older, your skill may go up or down. But at least for some amount of time, for some period of time, this AI would remain constant, right? So, we are assuming that individuals are different in terms of their skill. Okay. So, how will you accommodate the fact that individuals are different? Applying our knowledge of dummy variable, we can simply assign a dummy, one dummy for each and every individual. If I have n number of individual, then I can put this one, YIT equals to beta 0 plus beta 1 XIT plus, let us say, A1 plus A2 A n minus 1 plus UIT. So, that means if there are n individual, I will assign only n minus 1 dummy. And these dummy will capture that individuals are different, because we are giving different intercept for different individual. When you are talking about the first individual, all these items will take the value 0. So, the intercept will become beta 0 plus A1. For the second individual, it will become beta 0 plus A2, like that. So, by assigning one dummy, one for each individual, we are considering the fact that individuals are heterogeneous. That heterogeneity is captured by inclusion of several dummies in our model, right? Now, what Stata is reporting is actually, the Stata is reporting in Stata the constant term is actually AI bar. So, instead of reporting so many dummies, since we are asking Stata to estimate this model, that means the modern version of fixed effect model, additionally Stata is estimating the older version also and reporting what is the value of AI bar. So, that means the mean of this unobserved effect. So, from this we can actually understand what is the average skill of this individual. So, this AI bar, which is actually equals to then YIT minus beta 1 xi t bar, something like that. Okay. So, this is how Stata is calculating the older version of the fixed effect model also and reporting AI bar in the model. Okay. Is that fine? So, now if you go back, then you see that this constant is nothing but AI bar, the average value of the intercept. So, when we estimate, we will get several values of this coefficient. We will have a1, a2 dot 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 an minus 1. If we take average of all these, then that is nothing but our AI bar. That is nothing but our AI bar. Okay. So, Stata is actually not committing any mistake, rather Stata is estimating another version where AI is considered as a parameter. That means, what we are doing here, we are assigning dummy for each and every individual. That is why this older version of fixed effect model is also known as least square dummy variable model. Least square dummy variable model. Okay, or in short, it is also known as LSDV. Okay. So, this is how we can actually explain the coefficient. But then in this model, if you look at, there are 3 R square. 3 R square. So far, whatever model we have estimated, we used to have only 1 R square, one goodness of fit measure. But this is the first time we are getting 3 R square in a model after estimation. So, how will you estimate those 3 R square? Okay, how will you estimate the 3 R square, and what is actually the meaning of those 3 R square? The first R square is called within effect R square. So, within R square, within. So, what is this within R square? It is coming from this same model only. Yit minus yi bar is explained by xit minus xi bar. So, that means, since we are explaining yit minus yi bar with the help of xit minus xi bar, we already explained that this model is known as within effect model. The R square coming from this within effect model is known as R square within. So, this is the R square. R square within is R square, which is derived from the within effect model. Okay. Now, there are 2 other R square which is between and overall. What is this between R square and what is this overall R square? That we will discuss in our next class. Okay. There are several other important features of this fixed effect model we will discuss in our next class. Thank you.